Okay, so let's get started. Okay. Okay, so now in this last 50-minute block, I'm actually going to switch gears and almost entirely use slides and just give you like a seminar. And the goal is just to, there were a lot of questions throughout, so I just want to get to the main punchline of, you know, all of these different things that we've learned about Floquet models, many-body localization, eigenstate order. You know, they all come together in a very nice way to give you this example of this many-body Floquet time crystal that was disallowed in equilibrium. So I really do want to get to that punchline in this set of lectures. So this last little bit is going to be in the form of slides, but if there's any questions at any point, just feel free to interrupt and then we can go to the board in that way, okay? So the theme of this talk is surprises from time crystals. Okay, so I'm going to give you 3 main surprises that have come out of the study of time crystals in recent years. Okay, and you know, so I'll this, as some of you may know, is actually a topic that in the last 4 or 5 years has been very, very active, and I want to tell you some of the big the main surprises coming out of it. Okay, so the theme of my talk is inspired by this wonderful book by Peierls. We just learned about the Peierls theorem. Okay, so what he tried to do, this is in the preface of the book. He says, I have tried to collect examples in which the outcome of a calculation is different from what one would have guessed originally, or cases in which the solution turns out to be much simpler or much harder than one at first imagined. In all cases, it is clear that there would have been no surprise if one had really understood the problem from the start. Okay, so the case of time crystals is really a case in point of this quote, where, as is often the case in condensed matter physics, a number of simple ingredients came together to give rise to a whole that was much more complex than the sum of its parts. Okay, so to get started, let's start at the beginning, which is what is a time crystal. Okay, so a time crystal is an infinitely long-lived clock. Okay, so just like a spatial crystal, you know, so when you have spatial translation symmetry, the laws of physics look the same whether you do your experiment here or there or in Munich. But in a spatial crystal, the crystal breaks the continuous spatial translation symmetry of space, and its atoms are arranged in some regular pattern. Okay, so likewise, if the laws of physics are time translational invariant, a time crystal breaks this time translation symmetry and represents the emergence of a spontaneous clock in a system. Okay, so specifically, a time crystal requires your system to show some spontaneous motion that is periodic in time. But in general, you can get various ways in which you break time translation symmetry. You can get time glasses, time quasi-crystals, what have you. Okay, so one thing that's important to emphasize is that when I'm thinking about defining a time crystal, I really want to be, it's fundamentally important to think about macroscopic and conservative systems. Okay, so why is macroscopic important? Because few body systems routinely break time translation symmetry and exhibit recurrences or revivals. Okay, if you have a single spin degree of freedom in some magnetic field, the spin is going to show Rabi oscillations, it's going to show some time dependence, but we don't want to call every system with 1 spin or 2 spins a time crystal. Okay, so when I wrote this equation here, you know, for how time dependence works in some set of eigenstates or in some state, you know, you have all of these different frequencies. And while if you only have 4 or 5 frequencies because you're working with a few body problem, then you'll always get these kinds of quasi-periodic revivals. Okay, so if you really want to define a new phase of matter, we have to be thinking about macroscopic systems. And then conservative is important because battery-operated clocks are ubiquitous, right? You can, if you want to allow for systems that are not conservative, just go on Amazon and buy yourself a clock, right? And that you can call that a time crystal. Okay, so that's the setting in which we'll be thinking. And the first and biggest surprise, you know, my talk's going to go through 3 surprises. The first and biggest surprise is that time crystals exist at all. Okay, so what I just told you is that this time crystal is a macroscopic, conservative, infinitely long-lived clock. Okay, so this is a system that spontaneously pulses forever without any feed of energy. Okay, so the quest for such a clock, of course, goes back to age-old ideas for perpetual motion machines, all of which were rejected even before the laws of thermodynamics that oppose such motion were formulated, okay? And the basic objection comes from the first and second law of thermodynamics, okay? So the first law of thermodynamics tells you that perpetual motion needs a source of energy, okay? If you want to build your perpetual motion, if you want to buy a perpetual motion machine on Amazon, you should make sure that, you know, batteries are included, okay? The second law tells you that even if somehow you manage to sidestep the first law of thermodynamics, say by working in a frictionless setting, in some like ideal bell jar, you know, so you've done everything that you can to get rid of the dissipation of energy. The second law tells you that macroscopic systems head to entropy maximizing equilibrium states, okay? So usually when you're thinking of phases, you're evaluating things in equilibrium states, but the definition of a time crystal is a system that never reaches equilibrium, okay? So if you have to have this kind of time crystal in phase, you necessarily need some way of getting around the second law of thermodynamics that drives your systems toward time-independent equilibrium states, okay? So, okay, so this right now just seems like a no-go. You know, you either have the first law or the second law, but we're still here. So the reason is that there are various exceptions that are known and that can be formulated, okay? So let's do a very simple example that illustrates how these two laws of thermodynamics prevents a time crystal, okay? So you may ask, like, if you want to get some kind of perpetual motion or some kind of time crystal, why don't I just work with a large pendulum, okay? So if you have a pendulum like in your grandfather clock, it has some bob, okay? And the bob of this pendulum is made up of macroscopically many atoms, okay? In our thought experiment, we can say that we can make the bearings frictionless, we can stick it in a vacuum bell jar, and then you have this large pendulum with no dissipation. And normally you would think that, yeah, you know, if you have this pendulum in this vacuumless bell jar, it's just going to keep oscillating forever, okay? This is a macroscopic object, so is this a time crystal, okay? But the point is, again, it's important to think of not just this macroscopic system, but really a macroscopic many-body system to get something non-trivial, okay? So in your pendulum, if you thought of it as exactly 1 degree of freedom that was oscillating forever, okay, then indeed you're right. It will oscillate forever, but that's like what we were discussing earlier. You know, it's a few-body system. It's just a one-body system. Even though you had this macroscopic bob, in your mind you were thinking of it as just 1 center of mass degree of freedom, okay? But if you genuinely treat this pendulum as a many-body problem, with all the different atoms having their own internal modes, okay, then what you'll find is that over time, with the equipartition of energy, the energy that's in the center of mass mode gets distributed over these many numerous internal modes of your pendulum, and eventually it will come to rest under the second law of thermodynamics, okay? So a many-body pendulum cannot go on forever, even if you get around the first law of thermodynamics, okay? So a lot of examples that have been written down recently in the literature on time crystals in this setting and that setting, you know, they're really mean field time crystals in some sense, okay? So what they do is they take a system which naively looks like it has many degrees of freedom, but then they get rid of all these other degrees of freedom in some way and ultimately just isolate a single center of mass mode that looks like it's oscillating forever, okay? But if you actually put all of those back in, then this will come to rest and second law wins, okay? Okay, so how do we get around this tendency of going towards equilibrium? Wilczek in 2012 had a very nice idea, which really got this whole enterprise started. So he said, okay, what if I consider time-independent Hamiltonians, which are conservative quantum systems, in their ground state, okay? So if you're in the ground state, then the second law doesn't apply, right? This is U minus Ts, T is 0, so he wanted to think about ground states. And the picture that he wrote in this toy model in his mind was that he had a superconducting ring which was threaded by some fractional flux, okay? So then there's some persistent supercurrent. And he said, okay, so now if the ground state has some soliton or charge density wave, this would get dragged by the supercurrent and it would see oscillations, okay? So this was the setting that he had in mind. And an immediate objection that you can come up with is that, well, you know, if you're looking at one-point observables, if you want to look for some time-dependent observable in some ground state of the system, well, then that has to be time-independent, right? Because every ground state is a time-independent state. Every eigenstate is a time-independent state, okay? So this is something that you can immediately object to, but you can immediately also answer this objection by saying, well, this is true even for conventional symmetry breaking, right? So when we were doing this Ising model, if you started with symmetric states, which were your cat states, and you measured one-point expectation values, those were going to be 0, okay? But what you do then is look at either two-point correlation functions or perturb with weak symmetry breaking terms, and you can use that to define order, okay? So the same thing can be done here. Because this is still pedagogical, you know, just to be very, very explicit, we know that in a symmetry broken phase, the macroscopic equilibrium state of the system is non-invariant under the symmetry transformation. So in the Ising model that we were discussing, you had an all-up state, and this was not invariant under the Ising symmetry because it gets mapped to the all-down state, okay? So this implies a degeneracy or a non-uniqueness of the system's ground states, because you can start with one of them, you act with the symmetry operator, you get a different one, okay? And these two symmetry broken states are only degenerate in the thermodynamic limit, okay? Because again, in this Ising model, in any finite size system, your eigenstates look like these Schrodinger cat states, which are all up and all down, and it's only when you take the infinite size limit that these become degenerate with each other, and you can get either the all up state or the all down state, okay? So in any finite size system where your eigenstates look like cat states, if you go in and you measure your order parameter, which looks like a magnetization, then you get 0. On the other hand, you can go in and you can look for long-range order or in two-point correlation functions. That's what we did in the entire first part of the lecture. And in these two-point correlation functions, you can diagnose long-range order by looking for non-zero. You can diagnose spontaneous symmetry breaking by looking for long-range order in these two-point correlators, okay? Or the other thing that we could do is say, what if we added a very, very tiny symmetry breaking field, okay? And then you take the right order of limits, which is you take the system size to infinity first, you take the field to 0 second, and then you measured your Ising order parameter, and you find that you get something non-zero, okay? So this is again, and finally what you can do is measure the response of the system to a boundary symmetry breaking field, okay? So this is an argument again due to Peierls when he was thinking about symmetry breaking in an Ising model. He can say that, okay, you have your bulk Ising model, go in and in the boundary of your system, add in a small symmetry breaking field, so maybe your boundary is pointing up, and then look for your order parameter, which is your magnetization, deep in the bulk of the system, okay? So when your system has symmetry breaking, even if you add a tiny boundary field, it induces this huge susceptibility to ordering deep in the bulk, okay? So these are just three complementary equivalent ways of probing symmetry breaking in a conventional system, which is like a spatial or an internal symmetry, like the Ising symmetry, okay? So now we want to generalize this to the time-dependent setting for probing time crystals or time translation symmetry breaking. So for that, let's consider the simplest example, which is a harmonic oscillator, okay? So we know that in a harmonic oscillator, this is just one degree of freedom right now. We know that a one-point expectation value will be time-independent in any eigenstate. But we know that two time expectation values like x of t, x of 0, unequal time correlation functions, just like here we were looking at unequal space correlation functions. We know that unequal time correlation functions in the harmonic oscillator will show oscillations with the fundamental frequency of the oscillator, okay? Likewise, we know that this oscillator has a divergent susceptibility to being driven at its natural frequency, okay? This is analogous to the susceptibility to a symmetry breaking field. Okay, you can add in a tiny, tiny amount of symmetry breaking field, take the limit that the field goes to 0, but you can still get a non-zero magnetization out of adding in a tiny field, okay? So likewise here, there's a divergent susceptibility to being driven at the right natural frequency for this oscillator. And finally, the Peierls argument, which required you to put some kind of boundary condition in space and look for order deep in the bulk, Here you put boundary conditions in time, okay? So you can say that you can start from some initial state that is not an eigenstate of your system, but it's a superposition of eigenstates like a coherent state. And now you can ask, if you wait infinitely long in time, are you going to see oscillations, okay? So these are, again, 3 different ways of thinking about how to define time translation symmetry breaking. And in a harmonic oscillator, which for a one-body system does break time translation symmetry, you can see that these behave the way you would expect, okay? And now the big question for us when we're trying to define a macroscopic new phase of matter is whether these kinds of diagnostics can show you what you want for macroscopic systems, okay? So can you get this kind of behavior in a macroscopic many-body system? And what we know now is that there are various no-grow results from various people. You know, as soon as Wilczek wrote his paper, there were various people like Bruno, Nozier that came back and said, oh, this is not possible. And then Watanabe and Oshikawa really very formally first defined how to formulate a time crystal and then showed that you can't get this in an equilibrium system. Okay, so what Oshikawa and Watanabe did is they define an equilibrium time crystal as a system where if you measured this unequal space-time correlation function in an equilibrium state, in the limit of infinitely large systems and infinitely large spatial separations, you want this unequal space-time correlation function to show you time dependence. Okay, so and this correlation function is measured in some ground state or in some equilibrium state. Okay. So this is really probing spatio-temporal order, okay, because you're looking for long-range order in space and this kind of time dependence at infinitely late times, okay. And the reason for formulating it like this is precisely to exclude trivial cases like this, a single spin 1/2 in some magnetic field that's oscillating independently. They don't want just for you to build a system with independent oscillators, but they really want to probe this kind of long-range crystalline order in space and time, okay. So they wrote down this definition and then they used it to show that that you can't get time crystals in this equilibrium ensemble. Okay, so this definition is useful, but it's not exhaustive, and there's various exceptions that are possible. The first exception, which is perhaps the most familiar, is what you can think of as a symmetry protected time crystal. Okay, so these are systems which are very familiar to us. These are systems which have conventional symmetry breaking of either spatial or internal symmetries. And now you can kind of plug into those conventional symmetry breaking, into that conventional symmetry breaking and cause some kind of overall motion of your global order parameter, okay? So the simplest example of this is suppose you have some XY magnet in a magnetic field, okay? So you have some magnet, the magnet spontaneously breaks some internal symmetry, the spin rotational symmetry, and it gives you this macroscopic magnetization vector that's pointing in some direction. Okay, so that's your global long-range order in space. And now if you take this XY magnet and you stick it in an external magnetic field, then this global magnetization vector can show you precessions and you'll get this long-range spatiotemporal order. Okay, so that's a very familiar example. Another thing you can do is you can have a crystal which breaks continuous spatial translation symmetry. You can stick it in some eigenstate of total momentum, and then you're an observer here. This crystal is passing by, and you'll see some pattern like that. Okay, so these are just very familiar examples where if you have systems with conventional symmetry breaking, you can use that to get some kind of time translation symmetry breaking. The A.C. Josephson effect is another example that's in the same spirit. Okay. So let's move beyond that now, okay? A second exception that I hinted at yesterday, but I won't go into details of right now, comes from systems which display so-called many-body scars, okay? So these are systems which weakly break the eigenstate thermalization hypothesis. They don't quite reach thermal equilibrium, but there's various, there's a vanishing fraction of states that don't reach thermal equilibrium, and in those states you can take some observable and you can see some kind of oscillations forever. Okay, so there are classes of systems where you can prepare high temperature initial states, and in those high temperature initial states you do see oscillations. But now in the Oshikawa Watanabe setting, if you average over all states, then you don't see any kind of oscillations. Okay. The third exception is MBL time glasses, okay? So actually, from everything we discussed about many-body localization yesterday, you can now understand that all out of equilibrium MBL systems are actually local time glasses. So what you can do is if you go in and you measure in an infinitely large system, you can measure 2-point equal space but unequal time correlation functions, okay? So we know that in an MBL system, what we wrote yesterday was, where did my chalk go? Was that H basically looks like something like HI tau IZ plus JIJ tau IZ tau JZ and so on. These are your L bits, right? So, but under this Hamiltonian, if you look at something like tau x of t, you know that this is going to oscillate with some effective field that is set by all of these H's and all the expectation value of all the tau z's, okay? So in any many-body localized system, you can measure unequal time, equal space correlation functions, and you'll get some kind of glassy response. And it's glassy because there's a whole set of incommensurate frequencies that are all set by the local fields in your problem, and there's not just one periodic dependence, okay? So even though this is not long-range spatiotemporal order, even though this is only unequal time, not unequal space, this is not a trivial Rabi oscillator, okay? So this is not Oshikawa and Watanabe's definition, but it's still not a trivial Rabi oscillator because it's still a many-body system, right? I don't have just L different decoupled spins. This is a many-body system. And in a many-body system, generically, you expect dephasing and for things to settle down. So this is still a non-trivial example, okay? So for MBL, what we discussed in the first lecture is that long-range correlation functions in space can show you spin glass order. And now what I'm saying is that long-range correlation functions in time can show you time glass order, okay? And finally, the best-known exception is what we've been building up to in this series of lectures, which are many-body localized Floquet time crystals, okay? So this shows you correlated spatiotemporal order, which is long-range order in space and time, okay? So you really measure this kind of unequal space-time correlation function, and you find that you have time crystalline order in the time direction and long-range spin glass order in the spatial direction, okay? And this is something that happens in this intrinsically out of equilibrium setting of a periodically driven many-body system, okay? And this progress, the fact that we were able to define this time crystal, it really came out of work that was happening in this very different corner of physics, right? So when my collaborators and I were working on this, we really weren't thinking about trying to get a time crystal or about what Wilczek was doing. We were trying to answer this question that we've been discussing in these lectures, which is, what are the possible phases of matter in closed periodically driven many-body quantum systems, okay? And in asking this question, out came a phase of matter that actually furnished a realization of this phase that had deemed to be impossible, okay? Yeah.
But can you drop the conservative requirement?
Oh, good. So, very good. So the question is, if this is periodically driven and energy is not conserved, haven't I dropped the conservative requirement, right? So the point is that we're using many-body localized Floquet systems. So you're right that energy is not conserved, but in this MBL setting, there is no net energy absorbed from the drive, okay? So this MBL Floquet system doesn't heat up, right? So even though there is an external drive, there is no net absorption of energy from the drive. So it's not like the drive is giving you a net source of energy. It's just, you know, whatever gets pumped in gets pumped out, if you will. Okay, so that is important, yeah. Okay, good. Yeah. I mean, to talk about continuous symmetry breaking of an Ising symmetry, that's a discrete symmetry. Okay, so I'll comment on that in 1 second. Okay, so exactly. So now what you have is a periodic Hamiltonian with discrete time translation symmetry. That's the point that was just made. Okay, so normally if you had a Hamiltonian which was time independent, it had continuous time translation symmetry. Now you have time translation symmetry only by multiples of this period. Okay, so indeed, if you get something which shows like it's oscillating in time with the same period, okay, that's not breaking the time translation symmetry, because now your system as a whole is periodic with this period. And the analogous symmetry is actually corresponds to synchronization with the drive, right? So in a time-independent system, if you don't have time translation symmetry breaking, your observables equilibrate and become time-independent. In a periodic system, your observables synchronize with the drive and show the same periodicity as the drive, okay? So if you want to break discrete time translation symmetry, you need your observables to respond at some different frequency. So they can show period doubling or period tripling, right? But they have to respond with a period that's different from that of the drive to begin with. An example of this could be, you could have a lattice system already, okay? So in your lattice, you already only have discrete translation symmetry. You don't have continuous translation symmetry. And now you can have a phase which is like a charge density wave on this lattice system, okay? So then you had discrete translation symmetry of your spatial lattice, and your charge density wave breaks that discrete translation symmetry and can show you order at different wave vectors. So this is analogous to that. You have discrete time translation symmetry, and your system can break that and give you a discrete time crystal, okay? So we've already discussed this. You have a Floquet unitary, that's the time evolution operator over one period, and we're going to probe this. We're going to probe the dynamics of our system stroboscopically, so in multiples of the period. And to do that, all you need to know is the eigensystem of this unitary, which are the eigenvalues and the eigenvectors, okay? And what we'll find is that just like here, we could get an MBL spin glass, an MBL paramagnet. You'll be able to get a number of different Floquet MBL phases. Some of these exist only in the driven setting. There is no undriven analog of it, like these other phases that we've discussed when we were in our first lecture. And one example of this is a phase that we call the pi spin glass, for reasons I'll explain in a second, or the time crystal phase. Okay, you had a question. Sorry? So the question is, do you have goldstone modes in the system? So Manybody localization is actually not stable in the presence of goldstone modes, because that's a gapless mode that can destabilize localization. So we're not talking about U1 symmetries. So these are discrete symmetries.
No, because it's when you, for instance, put a system in a crystal, you have phones because you are breaking this thing. You have something similar?
There's no phonons here. It's an isolated. Yeah, so the phonons would be considered a bath. Yeah. No, but in general, if you just have a spatial crystal, you can talk about a charge density wave just in terms of the modulation of charge, right? So that's the spirit in which we'll be doing this. Okay. So the simplest way to think about it is to just take the disordered Ising model that we already studied and to now generalize it to a driven setting, okay? So I'm now going to be considering a time-dependent unitary operator. So I'm going to consider a periodic drive. And I'm going to consider one of these piecewise constant periodic drives just because they're easier to think about. That's not fundamental in any way, okay? So in the course of my evolution, I'm going to alternate between two different terms in this drive. I'm going to act with HZ. So the HZ is this kind of disordered Ising coupling. And there's dot, dot, dots. I'll come to what these are in a second. And then I'm going to act with HX, which is my disordered transverse field, okay? And then in time, you just repeat this stroboscopic pattern. These dot, dot, dots will refer to the fact that, right now, if this is all I have, then I have a non-interacting Floquet drive. But these dot, dot, dots in general will allow me to add in interactions and so on, okay? So for now to start, I'm going to pick these additional terms in the drive as a whole to commute with the Ising symmetry operator. Okay, so that again, in the spin language, corresponds to taking all your spins and flipping them. And if you do that, what you find is that you actually, for the non-interacting problem, you can solve this exactly. And you find that you get 4 different phases, okay? And these 4 different phases, this is a phase diagram that's exact. This is not a cartoon, okay? And it's plotted as a function of the average field and the average Ising coupling, okay? And you get 4 phases. 2 of them have long range order in space. They're spin glasses, okay? So they're like, the 0 spin glass is like the spin glass we already discussed. The pi spin glass is a new kind of spin glass, which has not only long range order in space, but also period doubling in time. That's what this pi will be referring to. So this is the discrete time crystal phase. And then we also have 2 paramagnetic phases. The first is the trivial paramagnet. Okay, that's this localized paramagnet again that we discussed already. And the second is what we call the 0 pi paramagnet. And this furnishes an example of a Floquet SPT, or a Floquet symmetry protected topological phase. Okay. Now, this phase diagram is exact for the non-interacting Ising problem. Okay. With interactions, all these different phases will persist, but the transition lines can get blurred as we discussed in response to a question that was asked. So what happens exactly at the phase transition between these phases becomes is more of an open question, but the existence of these phases persists even with interactions because of the persistence of MBL. Okay. Good. Right. The last thing I'll say is that we talked about how the non-interacting Ising model can be mapped to a system of Majorana fermions, okay? And we also talked about these edge modes, or the special energies in this pairing of E and minus E are energies where, for your Majorana modes, epsilon equals minus epsilon, okay? So in the static problem, this is only satisfied when epsilon is 0, but in the periodic problem, this is satisfied when epsilon is 0 or pi over t, okay? Because energy is defined mod omega. So these 4 different phases, when you map it to the Majorana language in the non-interacting problem, this corresponds to the 0 spin glass is the phase where you have a 0 Majorana mode present. The trivial paramagnet is no gapless, no edge Majorana mode. The pi spin glass is the phase where you have a pi Majorana mode present. And the 0 pi paramagnet has both 0 and pi Majorana modes, okay? So that's where this terminology comes from. Okay. So let's examine this phase diagram along certain exactly solvable lines that are easy to understand. Okay, so on this part of the phase diagram, what I've done is I've tuned my H to be 0. Okay, so you just turn the blue part off completely. You set your transverse field to be 0. So now your Floquet unitary just looks like the Ising model that we already solved. It's a disordered Ising model there. Okay. And what you find is that if you want to get the eigenvalues and eigenvectors of this unitary operator, you know that those are going to look like Schrodinger cat states. We already discussed this, right? Because it has Ising symmetry. This is just the ZZ term. So those are what all the different plus and minus cat states look like. And the eigenvalues are just phases corresponding to whatever that term happens to be. Okay. So this is representing the quasi-energy circle, right, because energy is defined mod omega. And what this is telling you is that all your many-body eigenstates are coming in these doublets. These are these degenerate pairs, which is the plus cat or the minus cat, or in Majorana language, this corresponds to the 0 Majorana mode being either occupied or unoccupied. Okay? Good. And, all right, so you can do the same thing for the paramagnets. I'm not going to go into that. But now, what you can do is, let's do this for the pi spin glass phase at a value of the transverse field, which is exactly tuned to pi over 2. Okay? Yeah.
What are the boundary conditions on the spin chain? Is it closed or open?
It doesn't matter, because in the spin language, it doesn't matter. In the that's if you think of it as a Majorana problem, and then it matters, but in the spin language, it doesn't matter. So to give you an example, like when you're doing the transverse field Ising model, if you do it with periodic boundary conditions in the fermion language, that depends on whether or not, that will control whether or not you have edge modes. But if you're in the spin language, then whether you have open boundary conditions or closed boundary conditions, you still have a double degeneracy of your entire spectrum for the plus cats and the minus cats. Right. So this does not matter, the boundary conditions, because we're working directly in spin language. Okay. So now you can tune your transverse field to be exactly pi over 2. One line of algebra tells you that if you have e to the I pi over 2 sigma I of x, which is this hx part of the Hamiltonian, okay, this actually exactly gives you this Ising flip operator. So your time evolution operator over one period now looks exactly like this Ising flip operator times this long range Ising interaction piece, okay? Or not long range Ising, just the Ising interaction piece. But if you want to get the eigenvalues and eigenvectors of this Floquet unitary, we know that the unitary commutes with the Ising operator, okay, this Ising flip operator. So the old eigenstates that we had, which were these Schrodinger cat states, they continue to be eigenstates of this new unitary, but crucially what changes is the eigenvalues. Okay, so if you have the plus cat that has an eigenvalue plus 1 under p, so the phase picks up a plus, and the minus cat has an eigenvalue minus 1, so these eigenvalues pick up this plus or minus sign. And when you take the log to get the quasi-energies which live on this circle, the quasi-energies, basically when you take the plus or minus log, you get something that differs by half the frequency. So that's the pi over t splitting, okay? So what you've done is, you used to have in your zero spin glass phase Schrodinger cat states that were exactly degenerate with each other, but now you have Schrodinger cat states that differ by half the frequency or pi over t in quasi-energy. So you have this pi pairing of cat states, that's what this pi refers to, and this pi pairing of cat states is what's going to give you your period double response, okay? So again, in Majorana language, remember we talked about how you get degeneracies in your many-body states by filling the zero Majorana mode or not filling the zero Majorana mode. Now you have a Majorana mode at energy pi rather than 0. So if you fill it or you don't fill it, you get many-body states that differ in energy by pi rather than being degenerate. Okay, so that's what this pairing is referring to. Okay, so you can immediately see at this exactly solvable line that you do have, that your system has spatiotemporal order. And how do you see that? Well, first you can look for period doubling. Okay, so if you start with a state which looks like this product state of z spins, and then you time evolve it under your Hamiltonian, what you'll find is that, well, you time evolve it under this piece, it picks up a phase, then you hit it with this piece, and all your spins just get flipped, right? This p operator is the flip operator in spin language. So as you keep going, you start with the spin, it gets flipped, you start with the spin, it gets flipped. So along this exactly solvable line, it's just trivial to see that you get period doubling, right? You start with some, you measure some observable here, it goes to minus itself, then plus itself. So even though your drive is periodic with period t, observables only come back to themselves at period 2t, okay? And you know you have glassy long-range spatial order, because if you go in and you measure these two-point correlation functions in your Schrodinger cat states, you either get +1 or -1, okay? So this is combining this spatiotemporal order. So good. But if this was the whole story, you know, this would be utterly trivial, because I've literally just taken a drive which explicitly comes in and flips all the spins. So no wonder everything is coming back to itself in 2 periods. You know, what's the big deal, okay? So the big deal is that this phase actually is extremely stable, okay? So there's various perturbations you can make of these different phases, and this pi spin glass or time crystal phase ends up being what we use the words absolutely stable, okay? So it ends up being stable to all perturbations that you can make, including ones that break the explicit Ising symmetry of the drive, okay? So let's start with a simpler class of perturbations. So what I'm doing is, along this line, instead of doing an exact pi flip, I'm deviating away from the line in this way. So now I'm doing rotations by about the x-axis by some angle which is pi minus epsilon, okay? So if you had a semi-classical picture in mind, what you would say is that you had a spin here, it picked up some phase, and then it got flipped not exactly, but by an angle which is pi minus epsilon, and then it got flipped again by pi minus epsilon, and then as you keep going, you keep accumulating that error, right? So in Fourier space, you would expect that you have 2 Fourier peaks at pi plus or minus epsilon. Okay, so that's what you would think about if you were just thinking of these as independent spins. Instead, what we find is that for this whole range of deviations, okay, even though naively it just looks like you should pick up this error, your response actually remains locked at period doubling, and you still have this peak, this Fourier peak at exactly pi over t, or half the frequency, okay? And the picture is that you have global long-range order that is stable. So even though you're making this kind of deviation, you still have your system that's globally long-range order, and that global order parameter can then flip or not flip, but you're not locally making this kind of errors that you would expect if you just had independent spins, okay? So this long-range spatial order is extremely important to the robustness of this time crystal phase, even when you have this imperfect angle, okay? And what's even more remarkable is that instead of just perturbing, this class of perturbations was still Ising even, I still had my Ising symmetry, but now you can go in and perturb with absolutely anything you want as long as it's weak, okay? And what you find is that even if you add explicit Ising symmetry breaking terms, your phase is still stable, okay? So, yeah.
How can we understand the sideband dependence on the drive? So like in the previous picture, so could you tell us why is this incoherence coming along in a sense?
Incoherence?
Like, so if you go to the spectrum, like the development of sidebands,
No, so this is when you leave the phase. So these different lines correspond to different values of this deviation angle epsilon.
Okay, the same. Okay, I thought about different.
Yeah. So what this is saying is basically that for a fixed range of different frequencies, different deviations epsilons, as you go along this line, while you're in the phase, you only get a response at this one frequency, which is pi over t. And then as you leave the phase, then you get a response at pi plus epsilon and pi minus epsilon, and that's this broad. So that's what this picture corresponds to. That's the beating when you leave this spin glass ordered phase and it looks paramagnetic, whereas this is the period double response, okay, which is locked. Good. So right. So now normally when you have a system with symmetry breaking, you know that if you have just a paramagnet or a ferromagnet, or you have this kind of zero spin glass phase that we were talking about, if you go in and you act with some explicit Ising symmetry breaking term, right, like sigma zi, right, you know that if you add a term like this, you've immediately lifted the degeneracy of your cat states and you've destroyed your long range order, right? But in this problem, what ends up happening is that your cat states actually are not degenerate. They're split in quasi-energy by pi, and this pi pairing gives this phase a remarkable degree of robustness, so that even when you add perturbations that destroy the Ising symmetry, this phase persists, okay? So all these other phases, the distinction between the zero spin glass and the paramagnet and the SPT, that's only sensible in the presence of the symmetry. But this phase, you can define and distinguish it from all the other phases without any symmetries present, okay? So I won't go into the details, but basically you can use the same kind of phenomenology that we discussed for Manybody localization and L bits, and you can show that even as you perturb this exactly solvable model, with the P and the ZZ, with all sorts of other generic fields in all directions, there is some local unitary transformation that relates the unperturbed and perturbed models. And then, just like before, you will get your Floquet L bits, okay? And then instead of having an explicit Ising symmetry like we got emergent L bits, now you get emergent Ising symmetry, even though you've explicitly broken the Ising symmetry. And so in these dressed variables, you end up with a drive that looks very much like the drive that you had before, okay? And the features that you need for this are Manybody localization and the pi pairing of the cat states, okay? So you're appealing to locality and unitarity as well. Like there is a topological property of the drives, which is the commutation relation between your dressed tau z operators and your Floquet unitary. This is, plus or minus 1. It's minus 1 in the time crystal phase. It's plus 1 in the spin glass phase, the zero spin glass phase. And this is quantized in these units, and this is some topological property that can't smoothly change. So even as you perturb away from your from this exactly solvable point and add all sorts of fields to it, what you end up with is with some emergent symmetry, and you end up with a drive that looks like that, which is still this Ising flip operator and this Ising even piece, diagonal piece in these dressed variables, okay? So, good. So let me skip over this, but the main upshot is that now, even after you have made all these perturbations, done all of this stuff, if you go in and you measure, if you measure correlation functions in your eigenstates and flow K eigenstates, so that's the notion of eigenstate order that we were discussing, you will end up seeing something that looks like it has this period doubled response even for long-ranged separated observables. But moreover, you know, these eigenstates are not something that you can measure, as we discussed. If you go in and you prepare just some generic initial state that any experimentalist can prepare, and you measure some observable at these stroboscopic times, what you will find is that there is a Fourier response which just corresponds to something uniform. You'll find one piece of it which is corresponding to a response at pi over t or period doubling, and then there's a whole bunch of other incommensurate glassy frequencies, and all of these go down as a power law in time. Okay, so if you wait very, very long time, starting from generic initial states, what you will find is a response that picks out this quantized pi over t piece. Okay, so this is very nice, because what I have told you is that not only is the phase very, very stable, but it also has these measurable dynamical signatures. Okay, so this immediately set the stage for various experiments to try to see this. Okay, so it actually happened very quickly. You know, there was a theoretical predictions, and then very quickly some experiments were done. And the third and final surprise that I'll talk about briefly talks about experiments, and it says that there's seemingly very universal experimental signatures even across a wide variety of platforms in these systems. Okay, so by now there are 4 experiments that have been done. 2 of these were in disordered systems. The first was in a system of nitrogen vacancy centers in a 3-dimensional diamond material. This was a very disordered sample. The second was a system of trapped ions in 1 dimension in Chris Monroe's group in Maryland. Then there was 2 different experiments on clean systems, so with no disorder. One was on an NMR solid, just a regular ordered 3D spatial crystal in the Yale group. And the last one was in a system of like star-shaped molecules of nuclear spins. So this was another NMR setup. Okay, so there are 4 different platforms with 4 very, very different experimental signatures, or 4 very different kind of setups. And what was really remarkable is that they all kind of gave the same signatures. Okay, so the protocol that all these experiments followed were similar. They acted with a drive which had some interaction piece and some imperfect rotation, like this pi minus epsilon that I was telling you about. What they found was that when your interactions were weak, you got these split peaks in Fourier space, but then as you tuned up your interactions to lock your system into some kind of global ordered state, you got this kind of response exactly at period doubling or at half the frequency. Okay, and all the experiments, they had a limited set of probes, but with this set of probes, they got a similar signature. So what's going on? Okay, actually, what you can let me actually just skip ahead because we're out of time and there's too many details. So let me just give you what all the 4 experiments are seeing. Okay, so the NV center experiment in diamond. Okay, this is the experiment with disordered diamond spins. It's in 3 dimensions with power law interactions. This is a system that's not supposed to have many-body localization. The interactions are long-range enough that even with perturbative Basco-Lena-Altshuler calculations, there's no MBL. So this model was not hoping to realize an MBL time crystal at all. But because of the disorder, what you can show is that the thermalization in the problem is very slow. It's only power law slow. So during the time that the system thermalizes, you can see some kind of oscillatory behavior, but with this power law decaying envelope. So that's what we call the critical time crystal. Okay. Then you have this system of these star-shaped nuclear spins, and this happens to be an example of what I was telling you about with the mean field time crystals. Okay, so even though this looks like you have 37 degrees of freedom and there's many, it's a mesoscopic system at least. In principle, in actuality, what happens is that you have all of these different satellite spins that are all interacting with some one central spin, and this effectively ends up looking like a 2-body problem. Okay, so with the 2-body problem, again, it's a finite size system, and you can get all sorts of oscillations. Okay, Then, these two models actually ended up being quite surprising. This kind of behaved as you expected. This, a few minutes of thought told you what was going on. These ended up being the real surprise because, the strapped ion system in one dimension, it is a disordered problem. And they had really started out trying to approximate an MBL time crystal. Okay, that was their goal because they had this very small system. It was perfectly controlled. They could put in disorder, and they tried to get this MBL phase. But what they did is that in this experiment, it's much easier for them to only put disorder in the fields rather than the Ising couplings, or rather than the J's. Okay, and you can show that actually if you do that, you don't actually get an MBL phase. All your disorder kind of gets echoed out. So if you look over a small period of time, as you did in the experiment, for a small class of initial states, it looks like you have oscillations, but this is a small enough system that you can just study it completely, and if you do that, you find that this order goes away in this system, and it realizes what's known as a pre-thermal time crystal and not an actual MBL time crystal. Okay, and the final surprise was this experiment on a clean, ordered spatial crystal, which was very, it's millions of atoms, long range interacting. There's no disorder whatsoever, so there's no MBL, okay? And it was initially thought that, okay, maybe this is seeing a conventional pre-thermal time crystal because it's a Floquet system. Even though it heats up, maybe it heats up and takes a very long time. But actually what we showed is that you can't describe it as a usual pre-thermal time crystal because the initial states that you were starting with were at very, very high temperature, and this actually furnishes a realization of a new phenomena which almost sounds like an oxymoron, which is a pre-thermal time crystal at infinite temperature. Okay, so you don't have to, I don't expect you to get all of these details, but the and even though they see these signatures, they're actually only probing the system with a very limited set of probes. And an unambiguous demonstration of an MBL time crystal is still an outstanding challenge. And there's various ingredients that we have now been able to sharply identify as a result of all these different attempts. Each of these experiments is an experimental tour de force. Like it's a really amazing. It's really amazing that they can do these experiments. Okay, and each experiment kind of added to our understanding and gave us a list of ingredients that we would like to have in an ideal incarnation of this phase, and there's various platforms that seem very promising in the near term to realize this. Okay, so I'll summarize with the main message that there's lots of rich physics to be explored in this out of equilibrium realm. We're only just starting to scratch the surface of it, and this last piece of work that I described was done in collaboration with this group of people here. Okay. Okay. All right.
Will you be able to repeat some questions after 2:30 in your office? Or you are leaving?
I think I'll leave. Yeah.
Okay.
Yeah.
So let us
Okay.
start this is one or two very short questions.
Okay.
Can this slide be available?
Yes. Yes. Yeah. Yes.
There are two more. One is when you use dissipation to get rid of these incremental frequencies and keep only a single space substance, one possible. And the other is actually unusual with the x-exact spin chain in a magnetic field.
Yeah. So I was just talking to Berislav about this yesterday. So he had some very interesting work showing that in an integrable system, this kind of generic dephasing that happens in your spectrum. So, one of the things, the reason why the pi spin glass works is that normally you have all these different energy differences, they're incommensurate with each other, and they dephase against each other. But in the pi spin glass, you have one energy spacing, which is exactly half the frequency, and all your eigenstates compared to that, so that doesn't dephase. And what Berislav's work showed is that if you have an integrable XYZ model, you can get these kinds of commensurate spacings, and you can look at observables that don't dephase. So that's really interesting because that's another example of how even without Floquet, if you have an integrable system, you can see these oscillations. Yeah. So this is published. So I put a paper out on it 2 or 3 months ago. It's on the archive. Yeah. 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 Yeah.
But for this kind of high first, it seems more to be relevant having this P operator, say, for simplicity in front of the unitary drive itself was not so important, but you could add any perturbation.
That's right. So you want to get a phase which has some Ising symmetry breaking. Okay, so you can, so what happened there is that even though you were adding perturbations, the dominant piece of it was the Ising interaction. And if you have the Ising symmetry breaking, even though it's of an emergent Ising symmetry, explicitly you've broken the Ising symmetry, there's an emergent Ising symmetry, you break that, you get some long range order in space, and now you can cause these locked patterns to kind of oscillate back and forth. So that's why you get the spatiotemporal order, but you really need kind of both ingredients to get the stability and to get all of this physics there. Yeah. Okay. All right.
It's time to stop here. Sorry.
No.